thank you to the organisers for the invitation to speak on what's a little bit more of a future-looking presentation. So the organisers asked me to give you the punchline at the start of the talk, and really this is the punchline from the talk, but I'll elaborate on each of these points as I go through the talk itself. Real-time soil testing isn't science fiction, but it is still just over the horizon, really, for most growers. The technology is really, where the technology is really going to make a big impact is in the sensor area. So it's not the carriage of the sensors, whether it's a UAV or a drone or a three-point linkage mounted, it's really the sensor itself. That's where the breakthrough needs to be made. And there's new sensors coming online all the time. I'll talk a little bit about some that we've evaluated and some that are available internationally. The really promising techniques are probably those, and again I will explain these, electrochemical, infrared and gamma sensors. And they appear to have the most application and the ones that are probably going to get adopted first and are being adopted at the moment. It's really important when new sensors come onto the market that you don't believe the marketing material, but we actually evaluate those properly. And really the success with the big four nutrients, N, P, K and S, is really quite elusive in terms of available nutrients in soil. And again, I'll explain why that is. So why do we need more soil information? Well, for precision agriculture, the key gap really is getting soil information at the same spatial scale as we get crop yield information through yield maps, through headers, and increasingly now crop nutrient maps through NDVI and other spectral methods. So we're getting very, very good spatial information, and everybody's got clients or has a property where they've got a yield map on the property, and you've got yields that might vary between 0.5 up to 4 tonnes per hectare. These are just data from Queensland looking at subsoil constraints, and you can see that some areas of the paddock are performing very well, other areas of the paddock performing poorly. So is it crop or equipment issues? It's not always soil variability. It could be something to do with the equipment. Topography, which is related to soil type, may vary across that particular paddock. And then obviously the variability in the topsoil conditions is going to affect crop establishment and growth. And a big realization over the last 15, 20 years that subsoil constraints can really constrain crop yield and access to water in the profile. So if we were going in with a soil sampling strategy on this, given that a complete soil analysis costs in the region of about anywhere between $80 to $120 for the full suite of analyses, and that excludes clay, silt and sand, which is quite expensive to do. You might go into that paddock and target some high yielding areas and some low yielding areas and hope that you can pick the relationship between the crop yield, in this case across the paddock, and the soil variability. So in that particular, if a targeted plan, you might have a fairly low cost that was achievable, but really if you want to get the same map of soil variability, you really need to go out with a grid sampling plan, and then the costs really start to blow out with traditional chemical analysis. So this is really the challenge for soil sensing, is to get techniques that can reproduce the grain yield map or the NDVI map with all the conditions that relate to crop productivity. So as I mentioned before, it's sensors that either have new capability or are much cheaper that are probably going to lead the way. Here we've got different sensors. We've got a handheld unit here, looks a bit like a speed gun, where you just press it on the soil surface. That's actually a near-infrared and a mid-infrared machine. Within 15 seconds you have a scan of the soil and many, many soil properties. I'll talk about the performance of that one. This is a new one that's come out of Israel, much, much cheaper, which claims to do similar things, and you can see it's much smaller, much lighter, and it's about 1/80th of the cost of this one. Veris Tech has been the company that's probably promoted on-the-go sensing the best in relation to equipment that growers can buy, and they've got various soil pH, EC, or organic matter monitors. I'll talk about those. And then if we want to go down the profile, again, we want to be probably not sampling soil. We want to be just scanning soil and getting the properties through a scan, and we don't actually need to take the soil back to the lab. So for the project that we had with GRDC, we were comparing some of the new infrared sensors that have come on the market, and these are the ones that we looked at. This is the one that is coming out of Israel at the moment. It's about $1,000, so it's very, very cheap. It hooks up to an Android or an iPhone. The idea is that the spectra will get beamed off to the company and come back with a recommendation or a prediction of the properties of that particular thing you're scanning. So they're hoping to sell it in supermarkets where consumers can scan fruit and products and test for contamination or spoilage or these sorts of things. This is a visible NIR scanner, more expensive, $80,000. Obviously not something growers are going to buy, but this would be then the target of specialist consultants who might set themselves up with that sort of instrument. These are two instruments from Agilent that have really got a good penetration into forensic applications and applications in the aerospace industry, looking at coatings on metals, looking at coatings on, or looking at forensic applications for drugs, for example, detecting anthrax versus other white powders, and they are now pushing into the agricultural sphere. And then Texas Instruments produced a little, it's called a nanoscan, again, very cheap for about $1,000, that purports to have the capability of some of these larger instruments and the desktop instruments. What is infrared spectroscopy? All those instruments work off this particular theory, effectively, where the infrared beam is just basically heat or light, is reflected onto the soil surface, and the reflected wavelengths are then captured by a little spectrometer. And the idea is that the soil components will absorb in various components of the spectrum, whether it's visible, near-infrared, or mid-infrared, and from that spectrum you can then predict soil properties. So one thing to note about this technique, it works on neat soil. So you don't have to extract the soil, you don't have to prepare the soil, it's just on the soil surface, so it's a surface scan. To test these particular instruments, so I'll talk a little bit about our evaluation of these infrared instruments, and then I'll talk a little bit about other instrumentation that's available. We took 80 soil profiles from the APSIM database that were fully characterized in terms of soil physical and chemical conditions held in the CSIRO National Soil Archive. So it was about 460 soil samples in total, going from the surface right down to 90 centimeters. We obviously have a very good database of soil properties for those soils, and we scanned all those soils with all those instruments under the same conditions effectively to evaluate their performance. These are the sorts of plots you can get then of the laboratory. So this is the laboratory measured parameter. In this case, it's clay percentage. And this is the prediction by the infrared instrument. So we draw a regression and we have a calibration there with a regression coefficient that gives you a measure of the goodness of fit. So it's important to remember that because we're going to be summarizing a lot of data using those R-squared values. We can also look at error at various parts of the scale, but just for this presentation, we'll do a summary on the R-squared values. The soil properties that we assessed were obviously important ones for growers: pH, electrical conductivity, clay, silt, and sand. That's not normally done in a routine soil test because it's quite expensive for laboratories to do that. But that particular parameter is really important for water holding capacity, and also if you're setting up an irrigation system to work out where to have your irrigation placed in the system. Exchangeable cations and cation exchange capacity, exchangeable sodium, that's important for soil structure, total and organic carbon and nitrogen, the drained upper limit and the lower limit for the APSIM model. So again, looking at the plant available water capacity of the soil, boron and chloride, which are a couple of subsoil constraints. Now, there's a lot of data in this slide, and I'll go through it slowly, but this effectively is the performance of the mid-infrared instruments compared to a laboratory instrument. The laboratory instrument is this one, and these are the two handheld devices that we were comparing. So the R-squared basically tells you the goodness of fit of the laboratory data to the prediction by the instrument. And first of all, you see they're all pretty good. Generally, we say above about 0.65, 0.7 is a good prediction for spatial variability of the soil in the field. So there's a wide range of soil characteristics that are being predicted very well using both the handheld and the laboratory instrument. And in particular, some of the ones that are quite expensive to get. the plant available water capacity through the drained upper limit and the lower limit, and sand and clay. Those are quite expensive analytes to do through a traditional laboratory, and these ones often done in the field with plant growth. The near-infrared instruments you can see quite different. Number one, the correlations are a lot lower for most of the analytes, and you can see big differences between the instrumentation. Unfortunately, the two cheaper instruments, the Texas Nano and the CSIRO, you can see performed very poorly for most of the analytes. So in this particular case, you pay for what you get for. You get what you pay for, sorry. Where the cheaper instruments, those $1,000 instruments, are really not going to be very useful for soil analysis in the field. And it means then that the more expensive near-infrared and mid-infrared instruments, they're going to be more than $50,000 to $60,000 to $70,000. It really precludes growers going out and thinking about buying those. It would have to be a consulting firm, a specialist consulting firm, which would go out and actually use those instruments. So one thing, though, is that miniaturization is something that's increasing in the instrumentation field. And in this case, miniaturization of the mid-infrared instruments did not affect the performance. So those small mid-infrared instruments were excellent, even better than the lab instrument in some cases. So as technology develops, those instruments are going to be becoming smaller and smaller. There's a new instrument coming from Agilent in the coming year, which is going to be smaller again, less expensive, and we're going to see, I think, those instruments performing better, much, much cheaper than the lab instruments, and probably then we'll get more penetration into agriculture. Those cheap NIR instruments at this stage, not really useful for soil analysis. And the reason for that is the spectral range that they scan isn't appropriate for soils. It might be appropriate for food, assessing food quality, but the wavelengths that we need for soil analysis are not represented in those instruments, so not to be used effectively for soils. And as I mentioned before, the instrumentation is still quite expensive at around $50,000 to $80,000, so it's not going to be something that a grower will go out and buy. Okay, what other instrumentations out there apart from infrared? Other techniques to get real-time soil information or soil information in the field? Well, gamma radiometrics has been around for a while. This is measuring gamma rays basically emitted from the soil from the isotopes of potassium, thorium, and uranium. Now, the potassium emission is obviously a very important one because it tells you then the total potassium concentration in the soil. And if you have a good calibration, it can give you the available potassium in the soil, but it's likely to be soil and site specific. So the uranium and the thorium can give you depth to clay, can give you percent gravel. And so it is useful because it's an on-the-go technique, and you can get lovely maps of the gamma rays emitting from the soil that you can then correlate to soil properties. So companies are using this, both internationally and in Australia, to do mapping of soils, and this is just Precision Ag in WA doing gamma mapping across their paddocks in WA. The disadvantage with the technique is that it relies on that local calibration of the gamma ray emission to the particular soil parameters that we're interested in, and that is going to be soil specific. Xray fluorescence, again, has become handheld. The instruments are about $80,000, so they are still expensive. It's really penetrated into the mining industry, where a lot of analysis now is done at the actual the bore where they're drilling. So it's a lab at the head of the drill, effectively. And as rock samples come out, they're scanning. It gives you total elemental analysis, so it gives you total iron, aluminium, will give you total phosphorus. It's not too good on some of the lighter elements like boron, magnesium, and sodium. But for most of the other elements, it does give you total concentrations. Again, that's not exactly what you're looking for in agriculture, where you want to get the available concentration. So again, you might need some soil-specific calibrations to try and infer that from other properties. But again, these instruments are getting cheaper and smaller with time. And I think this, coupled with some other sensors, could be quite a useful combination. Another technique called laser-induced breakdown spectroscopy. It's moved from the laboratory into handheld devices in the last 4 or 5 years. And again, this is a technique to measure total concentrations of elements in soil. The one difference to XRF is that it's very good for the lighter elements, so you can measure boron. And again, boron's one of those important subsoil constraints, at least in southern Australia. So we have one of these instruments at the moment. We're evaluating how useful it might be to measure soils in the field using a handheld device. Again, the problem is the expense. It's going to be $80,000 or more, so it's not going to be in the hands of every grower. Laser-induced breakdown is actually a technology that was used on the Mars rover, and universities in Europe are now trying to mount these sorts of devices onto the autonomous vehicles. The idea being the vehicle will go out and just automatically pepper the paddock and come back with maps of total elemental concentrations. And from that, you can infer perhaps available nutrient concentrations or depth to clay, clay content, or these sorts of things. So this is from the University of Strathclyde. Electrochemical methods are probably the thing that we need to focus on in terms of research for the future, because these are the methods that are going to give us the available nutrients in soil. So these respond to the particular ion of interest, either nitrate, ammonium, calcium, magnesium, chloride. It's an electrochemical response, and therefore you're getting an available concentration. The disadvantage being you need a liquid phase for these to work. So you either need to work in the soil pore water, or you need to extract the soil into water to do the measurement. Now that's difficult for on the go. For having a little extraction system on the go is difficult. It can be done. Veristech does it for pH, so it's not impossible. There's a new sensor that's been released quite recently in the States, which can, it's got its own power supply and its own data storage and its own electrode, and it's the size of your thumb. And the idea is that these can be buried in the soil and beam nitrate concentrations back to a central station. It hasn't been applied yet. I haven't seen any good evaluation of these sensors. Again, you have to be careful reading the marketing information. But it's worth, I think, Australia having a good close look at some of these new sensors from overseas to see if they could be used in our agricultural systems. Again, dependent on cost. We haven't seen a cost for these particular devices as yet. Then the analytical companies also make these little device sticks for engineers for measuring wastewater effluents and water samples. And again, there's no reason those couldn't be used in situ in the field for soils, because it's just an electrochemical measurement of the ion of interest. And these aren't too expensive, so they're going to be less than $1,000 for each stick. Other electrochemical methods have been commercialized overseas and are on the commercial market. One is the 360 soil scan, which again, it's an electrode method to measure nitrate in soil samples, requires an extraction, and the Solum no-weight nitrate, again from USA. Now, it's important we evaluate these, and Sean Mason will actually talk about some work they've done in South Australia, having a look at the soil scan 360 to see how it can reproduce laboratory nitrate analysis. Other ones that are out there, one released just recently in UK is called the Soil Care Soil Scanner, and it's a combination of a couple of sensors, electrical conductivity and infrared. The idea being, again, the price, couldn't see the price on the price list, but I think it's going to be around $40,000, $50,000. So again, it's not going to be home use or grower use. But working on the infrared principle, it's going to be able to predict a wide range of soil properties dependent on the wavelengths that are built into the device itself. And then CSIRO has a soil condition analysis system, which is a trailer-mounted system for scanning soil cores. It's got camera, visual, near-infrared, and gamma combined to actually map down the profile. Potassium, depth to clay, organic matter content, CEC, these sorts of things. That's Rafael Vizcarra-Rosell. Again, it's not something a grower's going to buy because it's quite expensive, but a specialist consulting firm could easily set up that type of instrumentation for scanning soil cores. Veristech is probably the company that's commercialized on-the-go sensing the best internationally. And they've got a number of on-the-go sensors. There's an automatic soil pH sensor to produce spatially variable soil acidity maps so that you can do variable lime rate. They've got an EC. I haven't talked about EM because I presume most people are familiar and comfortable with EM mapping. This is more the technologies that haven't quite penetrated the market as much. So they have an EC sensor, and they also have an infrared sensor on this, so it's a combination of 3 sensors to actually do 3 things at once and produce on-the-go maps. So where are the gaps then in the technology at the moment? Well, the gaps, I think, are still in that sensing easily available nutrient concentrations in soil. The electrochemical methods are the ones that are going to come closest. Infrared's not going to do it. It might do it for a small soil set, and some researchers might say it can do it for a small soil set, but really the universal calibrations are quite poor. So available nitrogen, so that's mineral ammonium and mineral nitrate. Available P, again, is a real big challenge because spectroscopically, phosphorus hasn't got any characteristic wavelengths at the concentrations we need to measure it at. Available K, probably gamma is the closest, or infrared, but really we need to have an extraction electrochemical method. And sulfate is also very difficult to do, and again, it's probably going to have to be an electrochemical method. So we're in a holding pattern waiting for the technology basically to catch up on those 4 major nutrients. So the current sensors on the market at the moment for those are either not robust, they're not accurate, or they're not cheap, and they're not fast, so they're not suited to on the go. So just to come back to the punchline, therefore, it's not science fiction, but it's not quite ready for on-farm deployment just yet, I think, by growers. We really need that sensor technology to develop more before it becomes affordable and robust to be mounted on every tractor, or so that we can get soil maps just like we get yield maps through a header. The electrochemical, infrared, and gamma sensors are probably the ones that are most promising. And so if we're going to fuse sensors together into a platform that can measure, it's probably those 3 that are probably going to be the ones to aim for. It's really important that we evaluate new sensors that come on the market internationally. And as I said before, the science really needs to focus on getting those big 4 for it to really make a difference to growers in terms of decision making. Other industries are embracing the technology quite strongly in terms of the handheld instruments. So portable XRF has really permeated the mining industry significantly. And portable infrared is now permeating the environmental industry quite significantly too, and this is to measure oil contamination in soils. So that's technology's been licensed, and consultants and companies are now buying those to do in the field measurements of those particular analytes. So there's no reason agriculture can't do it. I think the difference between mining and the environmental industries to agriculture is that we haven't seen companies who specialize in handheld spectroscopy really take off in Australia with an agricultural market in mind. I think it'll come. The commercial laboratories are setting up with the laboratory infrared machines, and I think it'll only be a matter of time before some of the precision ag companies, well, for example, the Gamma in WA has been adopted. I think it won't be long before we see some of these handheld units adopted by specialist companies that can come in and scan your soils and give you a really good 2-dimensional or 3-dimensional picture of your soil properties. And remember that the properties that these things detect don't change a lot, so you don't need to do it every 2-3 years. Clay content doesn't change much. Exchangeable sodium percentage might change if you put on gypsum. Organic matter content only changes slowly. So you may only need to do that spatially dense mapping of your soils once every 5 to 10 years, and then come back with the available nutrients more frequently to do that in-season decision making. Just like to thank GRDC for sponsoring the evaluation of the sensors which we looked at, and Mohsen, Martin, and Les who worked on the project with me, and thank you for your time listening.